Thanks for having me. It's nice being in California, even when it's cloudy. I'm going to be talking about semi-definite relaxation of k-means. Now, if you looked at the title in the program, you notice that it looks different from this. And it actually looks nearly identical to the next talk. And the abstracts also looked identical. We realized that we said we were going to give the same talk. And so what we decided to do was to split the effort. I'm going to give the setup, and Soledad's going to give the punchline, okay? So here we go. We got some sponsors. Okay, k-means problem. So someone gives you a bunch of points in Euclidean space, and your job is to cluster those points. For this talk, you're going to be told how many clusters. Okay, so let's say you get these points, and I say there's 3 clusters. You can kind of see how the points ought to be clustered, but we want something that a machine can accomplish. So we give the machine an objective. In this case, the k-means objective. Looks like this. The data points are xi. These are living in Euclidean space. The decision variable are these subsets of indices, okay? C1 through CK. So we're going to be partitioning the indices, and we want to partition the indices in such a way that minimizes the sum of squared deviation from the centroid of each subset. Okay? That's the k-means objective. It turns out that minimizing this objective, finding the partition that makes this number as small as possible, that's an NP-hard problem. So there exists ways of putting points, even points in the plane, for which we don't have a quick solution, a quick way of finding the optimal partition. But we have a heuristic, and it's really popular. It's hard-coded into MATLAB, Python, everything. Everyone uses it. It's called Lloyd's algorithm. Let's look at Lloyd's algorithm. So here we have what appear to be 3 planted clusters, right? We have the face of Mickey Mouse as well as his 2 ears, right? So we're going to run Lloyd's algorithm. We start with an initialization. So this big plus sign right here is a member of the set. There's also this big circle is a member of the set, and you can barely see it. There's a big X right there. Those are going to be the 3 initial centroids. We're going to carve out Voronoi regions from those 3 points, and that's going to partition the rest of the data. Then we're going to find centroids for those subsets of the data. So a centroid for red will be somewhere over here, a centroid for yellow will be somewhere over there, etc. Then we'll carve out Voronoi regions again, and we'll repeat. So it looks like this. You can see that yellow is swinging down to get the face of Mickey Mouse, and the 2 ears are covered by the others. Sooner or later, it settles down, it stops updating. And once it stops updating, you terminate the algorithm and you output the clusters, the partition. Unfortunately, if you start with a different initialization, you'll conceivably end up with a different clustering. And you could imagine your boss is asking for the best clustering, so you keep trying different initializations and you get better and better clusterings. But when do you stop? When do you say, okay, it's a pretty good clustering, let's call it good enough, boss. When do you know when to stop? Lloyd's algorithm doesn't tell you when to stop. So there's another thing you can do. You can take that initial optimization and pass to a semi-definite program. Let's talk through how to do that. First, I'm going to define a matrix. The rows and columns of this matrix will be indexed by the indices of our data points. Let's say I have big N data points. This is an n by n matrix. The ijth entry of that matrix is the distance squared between your two data points. Okay? I claim this identity, that my k-means objective equals this traced thing. Okay? So I have my distance squared matrix. I'm multiplying it by a sum of scaled versions of outer products. So 1 sub ct, this is the indicator function of ct. He's 1 when the index is in ct, he's 0 otherwise. Okay? The proof of this identity is simple. First, d times this matrix, a trace of that, I cycle, and I just get a scalar. It's lighting up all of the entries in D whose I and J entries both lie in CT. So I'm looking at a sum of these entries of D. What I can do is add 0 cleverly. I'll take, so little ct here denotes the centroid of big CT. Use that number, that vector. And I open the square, the cross terms cancel, and I get this, I can divide and add, I end up with this identity. Questions about that proof?
It only works in Euclidean space.
That's right. I'm very much using Euclidean space. So if I look at this matrix, I want to give you some intuition here. So shuffle the rows and columns so that the first so many columns belong to C1, and the second so many columns belong to C2, etc. Okay? When I do that, this matrix, so 1C1 times 1C1 transpose will be this component. It's this shade of gray because it's being scaled by 1 over CT. So when CT is bigger, this becomes, these numbers are smaller. Okay? So let's look at this matrix and collect some features. So each of these entries are 1 over C1, and there's C1 of them. So when I add them up, I get 1. That's going to happen for each of these rows. Okay? So this matrix times the all ones vector equals the all ones vector. If I look at the trace of this guy, I get a contribution of 1 from this block. I get another contribution of 1, total k blocks, so the trace is k. Each of these entries is either 1 over ct for some t, or it's 0. So all these entries are non-negative. And finally, it's a sum of outer products, so it's positive semi-definite. If I collect these convex constraints, I end up with this program. Instead of minimizing the trace of, or half the trace of d times x, where x has this combinatorial form, I can relax to just ask x to satisfy these convex constraints. And this is a semi-definite program. So we call it a semi-definite relaxation. Since we are minimizing over a larger set, a relaxed set, the number that comes out of this minimization is going to be smaller or equal to the original k-means problem. So if it's a tight relaxation, it'll tell you exactly what the clustering is. If it's not tight but close, it'll give you an approximation to what the best you could hope to do. This is the game we're going to be playing. Any questions?
Do you have any guarantees of how close it is?
Oh yeah. That's the whole next 2 talks are about that. Okay. Other questions?
So,
Yes, ma'am.
so even though the relation you showed in the previous slide, turning into this trace form, is only for the Euclidean norm, still this trace form also is what people solve for spectral clustering with other Ds, right?
Yeah. So if I throw this away, I'm essentially doing spectral clustering. So, and
That works in non-Euclidean.
they use this for graphs and such, yeah.
Works in practice, not with guarantees.
No guarantees.
And also the spectral, it's a different object. Spectral is not a way to try to optimize the k-means objective.
Right.
But
I was
it's a
just
different-
wondering if there's no way to go back from the spectral back to some. Anyway.
In fact, there's recent work to like throw, we call this the k-means STP, but they throw this STP at other like graph clustering problems. They replace D with some sort of Laplacian thing, and they end up with guarantees. So we came up with, we didn't come up with this. Some folks came up with this 10 years ago with the k-means objective in mind, but turns out it's useful elsewhere. So, good question. Any other comments? So I don't know if you know this, but solving a semi-definite program can be frustrating when maybe you have big data or something. So case in point, this is hardly big data, but 64 data points will cost you 20 seconds, whereas Lloyd's built-in implementation on MATLAB is a thousandth of a second. So there's some disparity here. What you can do, and this is pretty weird, you can hunt for what's been called a probably certifiably correct algorithm. Okay? So the model here is that there's some oracle that gives you the optimal solution with high probability. Okay? And all you have to do is tell when you're in that high probability event. So quickly certify optimality given this likely solution.
Wait, solution for initial problem of SDP?
The initial problem. Yeah, so you're actually solving the original NP-hard problem. There's a distribution floating around in the background, and that distribution is weighted towards easy cases, apparently. But that
Distribution over instances or over initializations?
Instances. We're not necessarily using Lloyd's algorithm as our oracle, but
What do you mean distribution of instances? It's distribution of the solutions, you mean? I mean instances
of the k-means problem.
But
Yeah, the data is random under
so
this.
why do you care of solving random data? Why would you care to solve k-means of random data? You care about your data, not about random data.
That's exactly right. So what we do here is we say we have an algorithm that doesn't look at the randomness, but we have guarantees that do look at the randomness. So I have something that works for general data, but I have a theorem that says, hey, even if the data is cooked up with this distribution, then I'm able to say with high probability, my algorithm that works in general works with high probability for that model.
This is worst case of all models. It will work for every model.
This is not a worst case analysis. This is an average case analysis for a particular distribution.
I mean, we can
I
have
just have a
worst
separate
case.
question how well this works for practical instances, right? I assume you will show that it works well.
In the second talk, you're going to see some really amazing results in that regard. I hope you have amazing stuff. Okay, so so the way this is going to work, the way this is even possible, is that it turns out that the convex relaxation, this SDP, is actually tight with high probability under a certain model of data. And it's possible to access this dual certificate that comes from the convex relaxation. You can get that quickly from an oracle solution.
I still don't understand the statement. I have my data, right? Now you have something which is on, if my data were generated randomly, it would have, your solution would have worked. How is it relevant to my data? My data could be worst case. You have something that's on every randomly generated data will work. Why does it work on my terrible data?
Right. So the guarantee we have doesn't talk about your data,
Okay, so
but our algorithm
yeah.
doesn't require randomness, just the guarantee. Yes, ma'am.
So you can say that this is a certificate that even you give your data and you can run this thing, and if it works, it gives you a proof that it's optimal. And if it doesn't work, it doesn't tell you anything. You can think of it that way.
So it's a verifier.
It's like a certifier. So you
have a certifier that I will give you a solution to the K-means problem on random, on arbitrary data, and it will tell me, is this an optimal solution or not?
Well, it can tell you if this is an optimal solution, or I don't know if this is an optimal solution.
Okay. So it could be optimal, but
it could be optimal,
and you wouldn't know.
It will tell you, but sometimes it doesn't know.
Okay.
So when we're going to talk about later is sometimes it can give you a lower bound when it may not be optimal, but tells you like a lower bound for the k-means value is this, and then there's like a 10% gap or something.
But where the randomness comes in is to say, yeah, sometimes it doesn't know, but under this distribution, it does know with high probability. And that's where the theory comes in.
Cool.
Sorry, just clarification. So your method satisfies like exact optimality, or it can satisfy like approximate optimality as well?
There's two parts. So there's a regime where we get exact stuff because we can, and sometimes the data is too messy to get exact, and yet you can still get approximate.
And I will know, so I know that like certificate will tell me it's within like 3% or something like that.
So there are going to be two certificates in the wild. This certificate we're playing with here is strictly exact. Soledad's going to talk about an approximate certificate. Mm-hmm. Collaborators, great. I'm going to tell you some stuff about cone programming. We're all going to get on the same page right here. Okay, so we got a set. The dual cone is the set of all vectors with positive inner product, non-negative inner product with everybody in that set. Great. Here's a primal program. This is a decision variable, x. Has some cost. I'm maximizing this inner product, subject to some vector thing living in one convex cone and my decision variable living in another convex cone. Okay? Convex cones include like the cones you're visualizing right now, ice cream cone, subspaces, zero vector, whatever. Okay. If you permute the letters, you get the dual program. And there's a reason that this is the right notion of dual program. And the answer is this thing called weak duality. So if you take the blue vectors from these two programs, you note that they lie in dual cones of each other. That means their inner product is necessarily non-negative. Same with the red vectors. So I got these non-negative vectors, and they each feature a minus sign. If I split over that minus sign and I move over to the other side, I end up with a sequence. I always have, if I'm feasible in the primal program, my value is less than or equal to the value of anybody in the dual program. Okay? So the maximum is less than or equal to the minimum. And it turns out that a lot of times it's equals, that the optimizer over here has the same value as the optimizer over there. So what that means is, let's say I have somebody that's dual feasible, and he has value equal to somebody who's primal feasible. Well, then what that dual feasible guy is he's certifying the optimality of that primal feasible guy, because his value can't get any bigger. He must be maximal. Okay? It's a dual certificate. This is a proof of optimality. So another way to unwrap that logic is called complementary slackness. So if I have an x and I have a y, x is primal optimal and y is dual optimal. Simultaneously, both of these things are happening. if and only if x is primal feasible, he satisfies these constraints, y is dual feasible, satisfying those constraints, and these inner products are exactly equal. X and y play nicely together. They satisfy complementary slackness. When these three things happen, that's equivalent to x and y being optimal in their respective programs. Any questions? Here's a picture. I find this picture to be helpful. So imagine you have your primal program living in one space. You have the dual program living in another space. You take their Cartesian product. This is the set of all points, x comma y, is primal and dual feasible. Okay? I have a set of points that play nice together. They satisfy complementary slackness with each other. What strong duality says is the intersection of these two sets are the set of points where the first coordinate is primal optimal and the second coordinate is dual optimal. Okay? Let me remind you what our game is. An oracle tells us something that is purportedly primal optimal. My task is to certify that he's primal optimal. So I get this point right here. I think it's this point. First thing I'm going to do is I'm going to check, is he primal feasible? Okay. Then I'm going to ask, hey, what's a y that plays nicely with that x? I want a y that's landing on this line. And then I'll ask if that y is dual feasible. If he is, then I just certified that what the oracle gave me is primal optimal. Does that make sense? So this was introduced by Afonso Bandeira when he was thinking about the stochastic block model. And it turns out that when you solve minimum bisection, you can pass to a semi-definite program, and there's a unique y that corresponds with x. Complementary slackness gives you everything you need to uniquely determine what y would have to be. And then you can just test if he's dual feasible. It's a semi-definite program, so that amounts to an eigenvalue problem. Yes, sir?
I'm trying to understand the high level. I mean, we have a problem that is NP-hard. It's NP-hard to approximate. So now you cannot achieve, you cannot break the NP hardness. You're not going to prove that P equals NP. So what are you going to? What kind of guarantee? I mean, how does it? Is it consistent with the hardness of approximation k-means? The result. What is the result in terms of how does it relate to the hardness of results that we know?
If someone gives me something that's optimal, I can certify that, I can prove that it's optimal in a lot of cases. That's the result.
Actually, in this model, like it's with high probability over the stochastic block model,
yeah, but
it will work. But for general graphs, it will not work. For the bisection problem, which is NP-hard.
Right. So for data mining,
it's distributed like the stochastic block. If the inputs are distributed according to the stochastic block model, then it will work with probability 0.9999.
So the distribution, you could say, is cooked up in a way that the hard instances receive vanishing probability. Great. Turns out that k-means is harder. You don't get a unique y. You actually have to make choices, and this is frustrating. We don't know what the optimal choice of dual certificate is for this procedure. In k-means case, that's an open question. Yes, ma'am.
Is there a classification of problems, like SDPs or whatever, in the setting when y is not unique versus when y is? Some classification saying these problems are easier than these others?
I wouldn't be surprised if so, but I don't know about it. Yeah. Soledad, do you know the answer to that? I don't know why I put you on the spot. All right. So there's a little technicality here with this method. So I told you, yeah, it's easy to test dual feasibility. It's an eigenvalue problem. How do you solve eigenvalue problems again? I use the power method, but that requires a random initialization. So it could be that I randomly initialize really close to a bad eigenspace. So the best I can honestly deliver is arbitrarily high confidence that the oracle gave me an optimal solution. Does that make sense? But this big O is hiding a spectral gap. But the number of 9s in my confidence, I get a 9 every iteration. So yes.
Do you have to use the power method?
Nope.
So would you get rid of this term entirely without power method?
So Afonso had a conversation with Dan Spielman, who said that, yeah, we don't know how to get around this. Like for numerical linear algebra, we have no idea how to get around that. So that's the extent that I'm aware of. Like, yeah, power method is not the only way, but at the moment, modern technology, we don't know how to get around this.
Wait, you mean like even in polynomial time?
You're trying to avoid to solve FTPs, right?
We don't know how to get around just if you want linear time.
Yeah, exactly.
I want linear time. Like, yeah, the quadratic is not helpful to me. Yeah. Speaking of linear time, this method works, and it's fast. So if the horizontal axis is the number of data points we're pushing around, and the vertical axis is the runtime. This is log scale, so you should think the slope is the exponent, okay? So k-means, this is kind of an eye chart. K-means plus plus in MATLAB is constant time until it's linear time, okay? It eventually becomes linear, great. If you run the k-means SDP, it's off the chart, okay? Too slow. So this is for 2 clusters, so you can intelligently invent a spectral method that is linear time, because it's low rank, you appeal to that, you get linear time. And what's even faster is running our PCC algorithm. So this is how you think about this. You take this amount of time to solve k-means plus plus. Now the oracle gave you a solution, and then you take this amount of time to certify that the oracle gave you the right solution. Okay?
This is an empirical table? Or
Yes.
Okay.
This
This is
is,
just on some data. That's the result that you get.
that's right. You can prove a theorem. This is a particular model of data called the stochastic ball model. I want you to imagine planted clusters. Okay, so I have balls, unit balls in Euclidean space. Each ball has a rotation invariant probability distribution. Okay, and I draw a bunch of points from each ball. Okay, now I throw the balls away. I just have the points now, and I need to run. Let's say the oracle tells me what the planned clustering is, and I need to certify, yep, that's right, that's the planned clustering using this PCC method. Okay? We have a theorem that says it works, provided the balls don't intersect. So the distance between 2 centers, if it's less than 2, yes, sir?
So there's this paper that came around the k-means plus plus paper, like, I don't know, the same year or something like that. They have a bunch of these hypotheses you can't actually verify. They essentially assume something about the clustering that you don't know if it's true. But under that, which are these really bizarre hypotheses, they got these bounds on the optimality of k-means plus plus would converge, or something like that. If you were to, and you're not asking for very much here, if you were to ask for impossible stuff, would you be able to still
So you're saying if I throw more stuff into my hypothesis, do I get the same conclusion?
Yeah, I
yes.
guess that was the case. You know which paper I'm talking about? 'Cause
No,
there's
do you?
two.
But there's a line of work of saying what is easy data for k-means clustering.
Yeah.
There's several types of assumptions under which you can show that k-means clustering becomes easy. The problem is that none of them is realistic. None of them happens in practice.
So this
And
this
this is
just-
also
this
completely
is really
unrealistic.
nice.
I mean, if your data, I mean, the question on such easy data, would other methods maybe also work fast?
So I want to disambiguate something. I'm not proving, this is not a theorem about k-means plus plus.
Oh, I know. But
Okay.
I'm looking at this as this is your data model.
Okay.
And they had another assumption, which was a data model that was kind of bizarre. It dealt with like cores. So like you'd have like a cluster that had some sort of property about distance from the centroid of it. It required you knowing the answer in
You're
order to
talking
verify
about
the
the
hypothesis.
Ostrovsky-Rabani's one?
Yeah, that one.
Yeah, so it's a very strong result.
Yeah.
And it implies that the data centers are 200 times
Yeah.
further away than the average distance of a point to its center. And under
Yeah.
this assumption, k-means plus plus or some version of
Yeah,
it
yeah, there
works.
was.
Right.
K-means plus plus won't work in this situation necessarily. You
Yeah,
can
yeah,
construct
but
situations where it won't.
you know, we have different easy situations and different algorithms will work on each. I mean, here you say k-means plus plus will not work on this.
Yeah, that's a result in the paper.
There exists a lame scenario where you have like this happening, you split that and group those.
Yeah.
Yeah. Okay. So
Maybe this is less easy, but still.
So I need them to not intersect plus some fudge, right? And the fudge decays with the dimension. All right, now it's romantic. So the SDP is tight, less romantic. Whenever this happens, so this is what I just told you. The SDP is tight from a previous paper with this threshold, and a more recent paper gave this other threshold. These are not comparable. Some are better than others in different regimes. We don't know what the best, what the correct answer is. Each one of these came from a different choice of dual certificate. Okay, it's an art form. We don't know how to resolve the art. You might guess that the correct answer is 2. Just make sure they don't intersect and you're good. That is wrong. So imagine 2 circles in R2 whose centers are separated by 2.08. Okay, and then solve k-means. I don't know if you see this, but the partition goes this way. That circle ate part of the other circle. This isn't uniquely optimal, obviously. That one also works. If it's 2.09, then the planted clustering is optimal. So there's a threshold here. It would be interesting to know if that threshold, like to what extent does that threshold persist in higher dimensions? Yes,
So I
sir.
have a question. So your certificate requires computing like top eigenspace of some matrix, right? Is this a dense matrix or sparse?
It ends up being low rank.
If your point's low in low dimensions.
Yeah.
Okay, fair enough. So basically your scale, like your chart with 10 to 8 points, they were very low dimensional, I assume. Otherwise you wouldn't be able to.
6 dimensions. Yep.
And what's the number of clusters here?
2.
Yeah, so then the problem is not even NP hard. I mean, 6 dimensions, 2 clusters, it's not NP hard.
Yeah. We were going for like, can we get linear time? Because k-means plus plus is linear, SDP very not linear. So, yeah. Okay. So, the stochastic ball model is really nice. Someone told me that recently. But it's pretty idealistic, right? What about messier data? What can you say then? So, I'm out of time, but I'm going to show you part 2 real quick. Part 2 says, yeah, the SDP still contains signal when you're. I got 10 minutes. Did we?
I think we started 10 minutes late. So.
All right, let's do this.
What do you think? 5? Okay,
We'll do 5. Yeah, that feels better. Okay, so we're looking at Gaussian mixtures. This is messier, right? Because you can have a point from one Gaussian land in the middle of another Gaussian. Good luck figuring out where he belongs. Okay, joint work. So let's think about that SDP again. Remember I had the trace was K, x1 equals 1, yada, yada, yada. Okay, some of these constraints tell me that X is doubly stochastic. Okay, he's a doubly stochastic matrix. So let's think about how I can leverage that information. Remember what xopt looks like when he's integral, when he's what we want him to look like. It's like this, right? What I can do, imagine P is the short, fat matrix whose columns are my data points. Okay, and I'm going to hit that on the right with the planted solution, say. What the first column of xopt is going to do is take the sample average of the data points in the first planted cluster. Okay. The second column is going to do the same thing, etc. So I'm going to have so many copies of the first centroid, empirical centroid, then so many copies of the second empirical centroid, etc. This is what clean data, what an integral solution would look like. That's how he would behave interacting with the original data set. Now what if xopt is not integral? Right? What if my data is so messy that the SDP optimizer is some other looking matrix? Okay? It doesn't look like that. So what I'm going to do is I'm going to show you, I ran the k-means SDP on this data set. Okay? I got xopt. This data set, this point is one of the columns of the 2 by whatever matrix P, right? And then I multiply that on the right by the optimizer of the k-means SDP. If it were integral, then when I morph these points into those things, I would get these guys morphing into their empirical centroid. These points would morph into their empirical centroid, and those points would morph into their empirical centroid. I'm going to show you the morph that comes from the SDP optimizer. It's going to look different. Pay attention. You're not going to be able to see this afterwards. You looking? Here it comes.
Snapchat.
Okay, so you can't tell right now, but these points represent a bunch of points. They all came together, and then I get some low rank noise. Okay? There is a lot of signal coming from this SDP. Can we harness it to say something about the true clustering? Okay? So you can think of this as a denoised version of the original data set. We're going to exploit that. We're going to try to estimate the Gaussian centers from this. Yes, sir.
So now we switched from k-means clustering to estimating mixture of Gaussians?
Right. So at this point, the rest of this talk, we're just looking at, we're proving theorems about how there's signal that the SDP optimizer captures. The next talk is going to answer the question you want to answer, which is how well does it approximate the k-means value? Yes, sir?
So is this doing mean shift?
Shift.
Mean shift is when you move everything to the centroid of the points in its neighborhood and iteratively do this. It looks like this process. That's mean shift clustering.
I can't answer. I don't know.
Okay.
Another question you could ask, which sounds a lot like that question, is what if you ran the k-means SDP on this? And the answer is it would go to one of these looking things. Okay. Kind of feels like what you're saying. Okay. So how do we prove a theorem? That denoising gives me some signal. So this represents, this is a symbol for the, I'm done? You got it. Oh, I am done. Look at that. You can do some cool stuff using stuff from Guidon Verschienen It's so awesome. You're missing out. Then you round, you get some cool stuff. And the next talk is going to answer your question. Any questions from you? No? All right, thank you.
Okay, so we have a short break, and then we'll talk about it. So.